This video is on the Floyd-Warshall all-pair shortest paths algorithm. Before this video, you need to know what graphs are and how they are represented, and the dynamic programming playlist has a few videos to watch. You should definitely know the stuff in the first two videos there, and hopefully the third one too. The playlist on single source shortest paths would also be helpful. Floyd-Warshall is a dynamic program, but to me it's never had the same feel as a lot of other dynamic programs. If you mess around with the problem long enough to get an intuition for the recursive idea of Floyd-Warshall, you can skip most of the standard dynamic programming steps. Here, I'll yank the recursive idea for Floyd-Warshall out of my nether regions and develop the algorithm using our standard dynamic programming template. Then I'll go back and show where the intuition for that recursive idea came from. Floyd-Warshall is really simple. You can code the final version in just a couple of minutes. To define our problem, we're given a graph with vertices 1 to n. We will assume that you're given the graph in adjacency matrix format. We want to find the lengths of the shortest paths from each vertex to every other vertex. Eventually, we'll also want to be able to quickly reconstruct those paths. We have our dynamic programming template, and our first step is to find a recursive approach to the problem. We're trying to find the lengths of shortest paths from each vertex to each other vertex, and I'm going to pull the recursive characterization for the problem out of nowhere. We will look for the shortest paths between vertices where the intermediate vertices on the paths must be numbered less than or equal to some value k. So, dk of I, j, will represent the shortest path from I to j using vertices only up to vertex k as intermediate nodes. I and j can be anything. So let's imagine that in this graph, for some reason, you want to find the shortest path from 2 to 10, but only using intermediate vertices from 1 to 9. There are two possibilities. Either you use vertex 9 or you don't. If you don't use it, the best path will be the same as the best path from 2 to 10 using only intermediate vertices from 1 to 8. Maybe that's 2, 1, 4, 7, 5, 10. Or maybe you do use vertex 9, in which case you need to get from 2 to 9 using only vertices 1 to 8. And then you need to get from 9 to 10 again with those same vertices. Those two paths concatenated give the best way to get from 2 to 10 using vertices 1 to 9, where you definitely use vertex 9. Those are the only two options. You use vertex 9 or you don't. You're only allowed to use vertices 1 to 9, so excluding that 9 node, these three paths only use vertices 1 to 8. The best path is whichever option is shorter. That gives us a recursive way to find that length. For our base case, if k is 0, there aren't any intermediate vertices you can use on the path because we number vertices from 1. So that means you have a direct edge. So if we want to find one shortest path, that would give us a recursive program to do it for any pair of vertices. On this small graph, to get from 1 to 2, we can run that code and see the recursive tree when it runs. The top two numbers in each node refer to the source and target vertices, and the bottom number tells us the top index we're allowed to use. The best way from 1 to 2 in general is the same as the best way from 1 to 2 using only vertices 1 to 4 because the graph only has 4 vertices. I highlight the shortest path from each possibility and the recursive calls that show the shortest path from 1 to 2 in the whole graph. For this small graph of 4 vertices, the recursion tree to find the shortest path from 1 to 2 already looks pretty bad. If we write a recurrence relation based on the highest vertex we're allowed to use, we can see how bad it is. Each vertex makes 3 recursive calls, which gives us order 3 to the n runtime. To make it slightly worse, we want every pair of vertices. This already looks insane. But it gets worse very quickly if the graph has more than 4 vertices. Up next, we can analyze the parameters and then memoize the algorithm. There are 3 changing parameters. The the source, the target, and the highest numbered vertex that you're allowed to use. That third parameter is what was hard about this recursive formulation. It isn't obvious. Limiting which vertices can be intermediate nodes on the path between your vertices when the vertices are arbitrarily numbered anyway, that's kind of out of nowhere. Until you create it, until you decide that it should exist, it's this hidden parameter not specified by the problem at all. Anyway, we have 3 parameters and can allocate a 3-dimensional table. Each parameter goes from 1 to n. The third parameter k can also be 0. And to make the base case look like the rest of the code, I've moved that base case right into the 0th D table. We want to solve on all ij pairs, so I'll first check the path from 1 to 1, even though that will just be 0 unless there's a negative weight cycle. Even though the graph is small and we're on our first tree, we can already see that parts of the tree get pruned. Any leaf that doesn't have a 0 as its third parameter got an answer from memoization. Now, if we crush that tree over to the side so the trees don't overlap each other, we can see that the next trees get pruned a lot more. And by the time you get to the last 5 trees, each is pruned to be as small as possible. They just look up the 3 values needed to fill in their top level call. If we want to go to our iterative bottom-up program to fill in any table location, you use the table to your left. So any order that goes from tables on the left to tables on the right will do. I'll go 1 table at a time, and within a table, row by row, left to right. That works. It gives us an order n cubed time and space algorithm, shown here on a graph with 5 vertices. Can we decrease our space? Well, when you're filling in table 3, you use table 2, but you don't need any earlier tables. So it's easy to go down to just using 2 tables instead of n. You alternate between tables to right while reading the other one. Can we go down to just 1 table? When you're filling in a location in the table, and you look at 3 locations from the other table, one is in the same row and column as your current location. Another is in the same row, and the third is in the same column. Using vertex 4 to get from 4 to anything, or from anything to 4, won't help you unless you have a negative weight cycle. So that row and that column won't change while you fill the 4th table anyway. Because they will have the same value in the 4th table as they had in the 3rd table, it doesn't matter which one you use to look them up. You can just use and update the current table. What about if there are negative cycles? If the path from 2 to 4 plus the path from 4 to 2 is negative, the algorithm will set the distance from 2 to 2 as negative, which shows a negative cycle. Once you detect one, you need to decide what to do with it, but Floyd-Warshall will work properly with negative cycles, even if you only use 1 table. This gives you an n cubed time, n squared space algorithm. That doesn't sound great, but remember, you're finding the shortest paths between n squared different vertex pairs. So the space for the algorithm is the same as the size of the requested answer. You can't hope to do better. Before we finish up the last step, where we figure out how to reconstruct any particular path, I want to back up. Where did that recursive idea really come from? The most common recursive approaches are divide and conquer and incremental growth. If we imagine a graph with 10 vertices, but remove the 10th vertex, you're left with a graph with 9 vertices. Imagine that you recursively know how to solve the all pair shortest paths problem there, including the shortest paths from 1 to everything. How does the 10th vertex change things? There are a few parts to it. First, you can find the shortest paths from each vertex to vertex 10. If we want to know the shortest path from 1 to n to 10, it will be one of the paths from the smaller graph plus 1 edge. So maybe it's the shortest path to 2 and then an edge from 2 to 10. Or maybe the second last vertex is 1 or 3 or 4 or 8. There are only 9, or n-1 possibilities. You don't know which is best, so try them all. That will take linear time to find the shortest path from 1 to the nth vertex. And you can do that from each other vertex in order n squared time total to get all of the shortest paths to the last vertex. Similarly, you recursively know the shortest paths from the first 9 vertices to vertex 1. And you can consider the first edge out of that last vertex to get the shortest paths from that vertex to vertex 1 in linear time, and to all of the other vertices in n squared time. After that, what do you have? The shortest paths from every vertex to every other vertex, except you don't use that last vertex as an internal vertex on any path. Paths can't go through vertex 10. That should look familiar. It's where we jumped in with our Floyd-Warshall recursive approach. We can update all ij pairs to allow them to use the last vertex in their paths in constant time each for a time n squared total update. Growing the graph from size 1 to n takes n cubed time total. The silky smooth simplicity of Floyd-Warshall is that they noticed you can recursively limit just the vertices you allow as intermediate vertices used within paths, while still letting yourself look at all source and destination pairs from the start of the algorithm. Recursion is a really powerful tool to solve problems. When you start working on a dynamic programming algorithm, you might not know it's going to be a dynamic program, but it's pretty normal to think about problems recursively anyway. If your recursive solution gives an exponentially slow answer, that's when you look to see if the dynamic programming approach works to speed it up. In this problem, you don't need to follow that template. If you recursively solve the problem in the incremental way we just considered, you get a slightly more complex but similar n-cubed algorithm that solves the problem without the template. If you then notice that you can use any source or destination from the beginning, you get the same final Floyd-Warshall program. Okay, what if after running the algorithm, you want to quickly reconstruct any particular shortest path? Probably the most obvious way is to store an extra table, and whenever you need to use some vertex k as a new highest numbered vertex on a path from I to j, store k. We'll name that table phi. I don't know why. 0 will indicate a direct edge, and any number higher than 0 denotes a vertex. The phi table is probably the most obvious extra information you can store, unless you're thinking about how you reconstructed shortest paths for the single source shortest paths algorithms. There, we used pi to represent the second to last vertex on the path, and we can do the same thing here. If you make a new path from I to j by concatenating a path I to k with a path k to j, the second to last vertex on that combined path is the same as the second to last vertex on the k to j part of the path. We can take a minute to watch that run. So there you go. An n-cubed time, n-squared space algorithm to find the shortest paths between all pairs of vertices in a graph. If there are any negative weight cycles, you'll see negative weights on the diagonal. Like Bellman-Ford, if you make those negative diagonal values negative infinity and run the algorithm a second time starting with those values, they will propagate to every appropriate source and destination pair. Without a negative cycle, each shortest path can be reconstructed in time linear in the number of vertices in it. The pi table gives an elegant way to reconstruct the path with one lookup per vertex on the path. The way I've written it, the phi table isn't quite as elegant. It has one lookup per internal vertex and one lookup per edge, so about twice as many. Still, either can be used to recursively reconstruct any shortest path in time proportional to the number of its edges. To test your understanding, what happens if we make this one minor change to the algorithm, changing that less than to a less than or equal? That's it for this one. I've got an appointment to get the hair on my back braided.